Okay, so now I'm going to talk to you a bit about factors that affect Sn1 and Sn2 mechanisms, and this goes along with 164, page 164 in your workbook, and I'd suggest that you follow along in there as I talk through this, because it kind of goes right with it. So the first thing that's mentioned there is the type of halogen alkane, whether it's primary, secondary, or tertiary. And again, let's remind ourselves about what exactly that means. It means you look at the halogen and you look at the carbon that it's attached to. How many carbons are directly attached to this thing right here, the carbon? This is called primary because this bromine is attached to a carbon that's attached to no other carbon molecules. It would also be considered primary actually if it was bonded to one other carbon molecule. That would be a possibility. This molecule is considered secondary here because this carbon is attached directly to two other carbon atoms. So this carbon is attached to two other carbon atoms, so it's considered secondary. And tertiary, this carbon, the carbon that the halogen is attached to three other carbons. So that's the difference between primary, secondary, and tertiary. When we're looking at this, mainly what we're going to decide is what type of mechanism is going to happen if this is going to undergo some sort of substitution reaction, either Sn1 or Sn2. When we're dealing with primary halogen alkanes, this is going to be Sn2 only. Basically, the primary carbons are not able to stabilize the carbocation that forms via an Sn1 mechanism. So look back at that if you forgot about how that mechanism works. But they just aren't able to do that. So these primary ones are going to proceed by Sn2 only. Now we're going to see that secondary are going to proceed by a mix, and there's no necessarily easy way to predict exactly which one it will do of both Sn1 and Sn2 mechanisms. And then the tertiary is going to be Sn1 only. It's just not possible for an Sn2 mechanism to occur because when we have to have a nucleophile coming in from this side, and it actually is completely blocked. Again, even though it may not look like it, it's essentially completely blocked. There's no room. It's called steric hindrance. An Sn2 mechanism can't happen with this tertiary carbon here. So that's the number one there on page 164 of the factors that affect the substitution is the type of halogen alkane, be it primary, secondary, or tertiary. Now the next one there, number two, is the nature of the nucleophile, the attacking nucleophile. And so if we're talking Sn2 mechanisms, what we'll be looking at is these nucleophiles going in here, attacking this carbon and replacing this bromine. Remember, Sn2 happens in two steps, but the slow step is the attack of the nucleophile, followed by which creates an unstable situation, and then the leaving group, the bromine in this case, leaves. The slow step is that first step, the collision. That's what takes the longest. So some nucleophiles are better than others. In other words, they would cause the reaction to be more likely to happen and occur more quickly. And basically I have a list here of 4 possible nucleophiles. Not the only ones, but these are 4 ones to sort of know about. They go from cyanide, the cyanide ion with the charge of -1, hydroxide with the charge of -1, ammonia, good old neutral ammonia, and good old neutral water. Of these 4, cyanide is the best able to attack. The water is the worst. And just some reasons, and sort of an introductory level of the reasons between things. Things that have an outright negative charge are usually better nucleophiles than things that did not have a negative charge. So these both have an outright negative charge, which is why they're towards the top of the list. Also, what we're looking for is nucleophiles where there's a less electronegative atom holding on to a lone pair. Because the less electronegative atoms, nitrogen is a little less electronegative than oxygen, are a little more willing to share, a little more willing to form a new bond. So nitrogen's a bit less electronegative than oxygen, so it's a bit more willing to actually share these electrons, where oxygen would rather sort of hog them for itself. That's how we kind of differentiate between these two. And same here, nitrogen's a little less electronegative than water. Remember, these are both not charged, so we rank them below these two. And the nitrogen's going to be a bit more willing to share and make this new bond and act as a nucleophile here. So that's the second thing that can affect these type of reactions is what's going to try to get in here and what we call attack this carbon. Cyanide of this list, cyanide is going to be the best at it, and water is going to be the worst. This is going to be the fastest. This is going to be the slowest. And so that's basically number 2 there. The third thing that affects this is the nature of the leaving group. The leaving group is, like it sounds, the group that's going to leave, the group that's going to be removed and replaced. Let's see if I can get this in the right spot. Sorry, it's a bit laggy here on my view anyway. In this case, like fluorine would be a potential leaving group and iodine would be a potential leaving group, because if there's going to be a substitution reaction, you know, if a little OH is going to come in here and this is going to leave, or a little OH is going to come in here and this is going to leave, fluorine and iodine are not going to react equally in this situation. In fact, iodine is going to be much more likely to react. The iodine as a leaving group is going to be much more likely to react. The reason for this is because it has to do with the strength of this bond. This bond is weaker. It means a better leaving group. And this is going to tie into a bunch of stuff that we've talked about before, but remember that smaller bonds are generally stronger bonds. Further, remember, if you think about your periodic trends, fluorine is a smaller atom than iodine. So this carbon-fluorine bond ends up being a fair bit stronger than the carbon-iodine bond. So if the bond is weaker, it means that it's more likely to, if the bond is weaker being this bond, if this bond is weaker, it means it's more likely to break, meaning a better leaving group, meaning a faster reaction, more likely to happen, all of that stuff. So of these two, iodine is going to be much more likely to actually undergo this reaction, is going to undergo it much more quickly and everything like that. That's what I mean when I say a better leaving group. I mean it is more likely to leave versus fluorine. And as far as your halogens, they're ranked just by their size. Fluorine at the top, it's the top of the halogens. Iodine at the bottom, it's the largest of the halogens. And the leaving group is ranked that same way. So the third step there just talked about some other possible leaving groups and ranks them, so you can look that over. But the basics of it comes down to how strong is this bond. The weaker this bond is, the more likely it is to leave. And that's essentially how it works. So that's our 3 factors. We've got the type of halogen alkane, whether it's primary, secondary, or tertiary. That tells us what kind of mechanism it's going to undergo, either Sn1 or Sn2. We've got the nucleophile, the thing doing the attacking. The better nucleophiles are more likely to undergo reactions. And then we've got the type of leaving group. Leaving groups that form weaker bonds with carbon, like iodine here, are going to be more likely to react than things that form stronger bonds with carbon, like the fluorine.